Thank you so much for joining us this evening. My name is Jacob Foster. I'm a computational sociologist of science, culture, and cognition at UCLA, and I'll be your moderator for this evening. As some of you may know, tonight's event, Reimagining the Social Sciences in the Age of AI, is embedded within a two-day workshop with a somewhat more prosaic title, Machine Learning, Theory, and Method in the Social Sciences. A dozen speakers with expertise ranging from conversational AI and causal inference to international migration and social stratification have descended on the Institute for Advanced Study to begin an intense dialogue that aims to promote transformational advances in both fields through conversation and, we hope, collaboration. The speakers are joined by members of the School of Mathematics and the School of Social Science, as well as colleagues from nearby institutions. The workshop participants are here with us in the audience tonight, and I hope that they will join vigorously in the discussion after our two public talks, at the very least to spare you from having to listen to more of me. This workshop and tonight's public lecture are the second in a two-part series bringing machine learning and the social sciences into dialogue. And we believe that this has been the first collaboration between the School of Mathematics and the School of Social Science at the Institute. This series has been incredibly stimulating, and I should acknowledge my fantastic co-organizers, Sanjeev Arora, distinguished visiting professor in the School of Mathematics here and professor at Princeton University, Marianne Fourcade, visiting professor in the School of Social Science and professor at UC Berkeley, and Didier Fassin, James Wolfensohn Professor of Social Science at the Institute for Advanced Study. The first event, which I hope some of you joined us for, on social and ethical challenges of machine learning, brought Pedro Domingos and Mary Gray to Wolfensohn Hall as public speakers for a vigorous discussion peerlessly moderated by Alondra Nelson, Harold F. Linder Professor in the School of Social Science. I will not even attempt to live up to the standard that she set. Our speakers, however, should intrigue and inspire you. Tonight, you will hear from Elizabeth Bruch of the University of Michigan and Tom Griffiths of Princeton University. Both speakers will address the intersection of contemporary machine learning and the social sciences, but from different and delightfully complementary disciplinary orientations. Elizabeth Bruch will kick off the evening with her talk on discovering decision rules in mate choice. Elizabeth is Associate Professor of Sociology and Complex Systems at the University of Michigan and a member of the external faculty at the Santa Fe Institute. The recipient of many prestigious awards and fellowships, including the Robert Wood Johnson Foundation Health Policy Fellowship, a fellowship at the Center for Advanced Study in Behavioral Sciences at Stanford, and the Robert Merton Prize from the International Network of Analytical Sociologists, Elizabeth is distinctive in her long-standing interdisciplinary orientation to scholarship in cognitive science and decision theory, her use of rich online activity data, and her emphasis on building cognitively plausible models of human behavior. Tom Griffiths will follow with his talk on human behavior as the next frontier in AI. Tom is Henry R. Luce Professor of Information Technology, Consciousness, and Culture in the Departments of Psychology and Computer Science at Princeton University. He, too, has received many prestigious awards and fellowships, including an NSF Career Award, a fellowship from the John Simon Guggenheim Memorial Foundation, and a finite but very large number of Best Paper Awards. Tom is the co-author of the book Algorithms to Live By, which I can recommend very highly. His work marries cognitive science and artificial intelligence, using methods from the latter to understand how humans are able to solve a range of forbidding but everyday computational problems, making predictions about the future, learning new causal relationships, or discovering how to divide objects up into categories. It should be an exciting evening and an exciting future as we reimagine together the social sciences in the age of AI. So please join me in welcoming to the stage our first public speaker, Elizabeth Bruch.
Thanks so much to Jacob for that warm introduction, and thanks to everyone for coming out. I'm going to talk to you today about decision rules, discovering decision rules in mate choice. And I want to start with some broader points. The past 15 years have heralded in the rise of so-called big data. I'm talking about the little data breadcrumbs you leave behind when you do Google searches or look for a partner online or try to find a job on link.com. A lot has been said about big data, but the thing that I really want to emphasize to you tonight is that there's an aspect of these data that I think is especially transformational for social science. And that's the fact that these data are process data. They're behavioral and they can provide insight into decision processes. This is in many ways fundamentally different from the types of quantitative data that have been previously available to social scientists. And I'm going to nail down that statement with a couple of examples. First, consider the question of residential choice. Social scientists, quantitative social scientists who previously studied residential choice typically ask people to provide a record of the addresses that they lived in at previous residences. Those addresses were then used to feed statistical models that could tell us things like, what is the probability that, for example, a white person chooses to live in a neighborhood that is a given percentage white? Obviously, that brings you a lot of insight, but it doesn't provide a lot of detail about the processes through which people select neighborhoods. Contrast that with something like the data that's available on something like Trulia, where you can literally see in real time not only what attributes people are looking at, but the order in which they're looking at them. For example, imagine that you saw someone who, having discovered that a neighborhood had schools below a given quality, never considered schools in that, or never considered housing units in that neighborhood, regardless of how wonderful their other qualities were. Similarly, these kinds of big data provide wonderful opportunities to get deeper insight into the types of opportunities that people are facing. Studies of mate choice have previously been forced to assume that the mate market is in fact the entire metropolitan area. But one can imagine, especially with spatially and temporally rich data, the discovery that in fact dating markets are dynamic. They change over time. For example, as you might move from your housing unit in Queens going into Manhattan on a Saturday night, and they also change in terms of space. So this kind of richness of process creates wonderful opportunities but also challenges for social science research. And one of the major challenges is that the statistical models that we are used to using were developed in an era where the prevailing data were surveys and administrative records. And as a result, we got extremely good at analyzing associations among variables, that is, attributes and characteristics of individuals, as opposed to trying to represent the underlying decision processes or activities that human actors were engaged in. So what I want to do with most of my talk today is present to you one attempt to develop a statistical model that really tries to grapple with decision processes, in particular in the context of what's observed in online dating. But to get to that, I want to start by telling you a little bit about what do we know about how people make decisions. And I'm going to talk in particular about a particular area of research that was valuable for me in developing this model. So there's a large body of work in cognitive science and decision theory that effectively tells us that heuristics are the primary tool by which people make decisions. Heuristics are problem-solving strategies that tend to produce efficient solutions to hard problems on the basis of some analysis of the structure of the problem. And if that sounds like a mouthful, don't worry, I'm going to make it more concrete in the next couple slides. But the main thing you should know is that heuristics, simple cognitive shortcuts, are a strategy by which people make decisions. And importantly, people decide what heuristics to use based on features of their decision task. So in front of you here, we have 4 different decision tasks: what neighborhood to live in, what health insurance plan to choose, what colleges to apply to, and what to order at a restaurant such as McDonald's. You might look at these and say these are completely different decision problems. But of course, we can also consider structural features of the decision tasks they might have in common. For example, you can imagine evaluating them based on the frequency of the decision, which might tell us something about the extent to which habit or what you've done before guides your next choice. And here we see that neighborhood choice, health insurance choice, and college choice are relatively rare occurrences. Of course, what you eat is a choice that you typically make every day. Similarly, we can ask, are these all situations in which you can pick whichever one you can afford? Is any option available to you? And of course, what we see in the case of neighborhood choice, well, sometimes. Certainly in the case of health insurance choice and in food choice. In college choice, absolutely not, because you have to be admitted. Whereas, of course, when you're going to buy a hamburger at McDonald's, the hamburger doesn't look at you and say, oh, I don't feel like being bought by you today. So in this case, you would expect that decisions in which you have to have some, there's a dyadic component, you're going to have some kind of strategic aspect anticipating the response from the other side. But in fact, I didn't choose these 4 examples at random. They all have something in common that it turns out to be pretty important for the rest of my talk. And if you can think about for a minute, what do you think they all have in common? Don't worry, I'm not going to ask you. But the thing that they have in common, it turns out, is that all of them involve a moderate to large number of choice alternatives, where moderate here can mean anything from 2 to 3 to 7, okay? So they all involve choosing from more than a tiny handful of choice alternatives. And it turns out that this has been a really rich area for the field of judgment and decision making. There's an enormous literature now on how people make choices when choosing from this moderate to large set. And a number of consensus items have emerged. First of all, it's widely agreed upon that when people are making these kinds of choices, they approach them in a series of stages. So you can think about the set of choices that you can make can be divided between sort of the set of all potential choice alternatives and the subset that would be explicitly considered, which is called the choice set. And it's from this choice set that you select your final choice option. Importantly, what people have found is that different decision rules guide the decision process at different stages. In particular, when you're deciding what to winnow down from the original set of all possible alternatives, people typically invoke what are called non-compensatory screeners. Effectively, they choose just 1 or 2 attributes, and they establish an acceptability cutoff on them. For example, think of yourself going to the supermarket to buy milk. You don't read the nutrition labels and the prices and the details of every single one. You establish some kinds of consideration cutoffs. For example, you might only buy organic milk or milk that's less than $3 a gallon, or whatever your cutoff is. Now, what's critical here about these non-compensatory screeners is that you may not even look at other attributes other than the ones that you're screening on. So even if you had an attribute that was wonderful on some other quality, you would never know. It can't compensate for that if you're screening it out of consideration. Once the set of alternatives has been winnowed down to a smaller number, people typically do engage in more compensatory evaluation, looking at a wider range of attributes. And that's what tends to yield the final choice decision. So one of our points of interest is, what are these decision rules? Another thing that's quite interesting, and a lot of this work comes out of academic marketing, is that in sort of experiments trying to understand how to change the way you make decisions, it turns out that interventions, where the intervention here is basically getting you to buy something, at the first stage, at the consideration stage, tend to have a much bigger impact than interventions at the second stage, which potentially has implications for things like public policy, and I'm happy to talk about that later. But the main thing is that this is a well-developed literature on sequential choice with different decision rules at different stages. And so it's an area that we want to build on when thinking about how to develop a model of make choice. So for the rest of my talk, I'm going to introduce you to some of the more interesting results from a paper we wrote trying to apply such a model to online dating activity data. And I'm sure everyone in this audience has heard of online dating. What you might not know is actually, as of 2017, online dating is the most common way couples meet in 2020. So what I put up here is a rather remarkable graph from a recent PNAS paper. And what you see is on the y-axis is the percentage of couples who met a particular way, and on the x-axis is the year the couples have met. And I want to draw your attention first to the red line, which is effectively the percentage of people who met online. And it really shows this sort of astronomical growth of online dating. In 1980, I believe 2% of couples met online. And in 2017, it was close to 40, pushing out other previously more common forms of meeting through friends, meeting in bars and restaurants. When I first started working on this project, a question I often got from my audiences was, well, this is online dating. What do people do in the real world? And so I think when I saw this, the thing I realized was actually this is the real world. This is how people are meeting. So that's online dating. What else do you need to know about online dating? Online dating is also structured explicitly as a multi-stage process. In fact, you can imagine you have all potential partners on the site, but nobody looks at everyone on the site. They have to make decisions about who to explicitly consider. And we're going to refer to that as browsing, the decision to browse a particular profile. Having browsed a profile, they also have to make a decision about whether or not they will write to this person. So part of our interest here is discovering the decision rules that guide the browsing and writing decisions. So first, who's good enough for me to browse? And then among those people who we've browsed, who's good enough for me to write to? The model that I'm going to talk about has a couple of different attributes that we wanted to preserve when we developed it. The first one is that, as we mentioned earlier, we want to capture distinct stages of the decision process with different rules at different stages. And the second thing was, recall I talked to you about compensatory and non-compensatory decision rules. Non-compensatory decision rules in dating are especially fun because they have kind of common terms. For example, deal breakers or deal makers. I won't go out with anyone over 40 is an example of a deal breaker. Or I need to date someone Jewish. A deal maker is having a PhD is a huge plus. Or other ones that you can imagine. Turns out deal makers are actually relatively uncommon in dating, but they do exist for very small subsets of the population. In any case, deal makers and deal breakers were definitely something we were interested in finding if they existed in this model. Another thing was, I'm not going to have time to tell you very much about the data set I used for this, but it was a marriage-oriented site for a somewhat homogeneous population. However, we had a hunch that there was a lot of heterogeneity or variation in the rules or strategies that people were using on this site. Even after you condition on and take into account attributes like people's age and their education, there still may be quite a bit of heterogeneity in strategies, and we wanted to capture that. Another thing that we cared about a lot was establishing precise cutoffs. Now remember that when we talked about non-compensatory rules, they often invoke cutoffs. But cutoffs are interesting for another reason, which is that when you think about dating rules, and I'll get to that, I'm not going to say much about that now because I'll talk about it when I present the results. Dating rules often invoke sharp cutoffs in terms of acceptability criteria or other ways of governing behavior. And finally, we wanted to estimate these rules not in a way that was more hypothesis-driven or putting things into the model, but we wanted the model itself to just uncover what those rules are based on what people did. So machine learning with rules learned from the data. I'm not going to say much about the equations, so don't worry. I just want to call your attention to a couple of parameters in here because I'm going to explain what they mean visually, and I just want you to note them. You'll see that there are two things I'm going to refer to as cut points. Those are those gammas. And you're going to see that there's 3 slopes. Those are the betas. That's all you need to know about this equation, because now we're going to jump into some pictures. Basically, we want to know, how do people assess desirability based on attributes of people on the site? Remember, we talked about compensatory and non-compensatory rules. And I said my model's going to tell you whether people are using compensatory versus non-compensatory evaluation. So what does a compensatory rule look like? Well, here's an example. You can see that those same parameters are represented here with slopes and cut points. You could imagine that you have a compensatory rule for facial hair. And what that means in practice is that a little facial hair is nice, and a lot of facial hair is nicer. But, you know, nobody's like getting a deal breaker or a deal maker on facial hair. It's a nice, it could be nonlinear, but it's a relatively simple relationship. Contrast that with something like how people typically respond to something like age, where you can imagine that you're someone who likes younger people. You like to date younger people. However, you'll never date anyone under 18. And you really don't want to date anyone over 40. And I put this, you'll note that the beta 1 here is basically going to minus infinity, like never will you date anyone under 18. But you know, this other beta 3, it's not minus infinity, it's just really sharp. And that's important because when we started developing this model, we found previous examples of people who developed statistical models of compensatory and non-compensatory evaluation. But one of the ways people do this is they basically look at whatever, for example, what is your cutoff on age? What's the oldest person you're willing to date? And whatever that is, that's your cutoff. And that actually doesn't work for online dating because people's behavior on online dating sites is incredibly noisy. You're at work and you're bored, so you're browsing profiles, or you really don't want to ever date anyone over 40, but your grandmother's on the site, so you write her an encouraging message. There's lots of noise in these data, and one of the challenges for us in developing this model is it had to kind of parse out the structure within that noise. And so we would refer to these as like a near deal breaker. It really would take a lot. Basically, it's impossible, but it's not totally impossible to overcome this. Finally, I said there was the existence of deal makers. This is what a deal maker might look like in this kind of data. You can imagine that if you have a deal maker for income, perhaps a woman who makes over $50,000 is attractive, but boy, if she makes $1 million or more, you're writing to every single one. And there really are people in our data who seem to have written to every single person in their city who says they made more than $1 million. Whether they did, that's another question. But that was it. That seemed to be their strategy. So this is just to give you a flavor for the types of behaviors and how they actually feed into the parameters in the model. I'm not going to say much about the estimation of this model because it's not the most interesting part of the talk. I will say it was a challenging process, and I'm happy to talk about that later with anyone who wants to hear about that. But mostly I want to jump into the results. So we estimated this model, and I'm going to present what looks like a complicated figure. It's a set of complicated figures, but I'm going to break it down for you. So here's the first set of results. Now, remember before I said that these models, we believe there was a lot of heterogeneity, there was a lot of variation in people's strategies, and we wanted to allow that variation to occur naturally. What we found from the model was that essentially there seemed to be in these populations 5 distinct strategies that men were using and 5 distinct strategies that women were using. We didn't build that into the model, but it was what the model told us based on sort of the statistical results that came out of it. And so each of the lines here represents, each of the colors refers to a particular class of people that is characterized by a distinct strategy. Recall that I told you it was important to have different decision rules at different stages. So the left-hand and right-hand panels effectively tell us what are the decision rules at the browsing stage and what are the decision rules at the writing stage. And the top and bottom panels give us the results for men and the results for women. And both of the slides I'm going to show you will have the same structure. So what we see here is effectively how do men and women respond to age at the browsing and the writing stages as a function of their age as well as the age of their potential partners. And the first thing to notice here is that there are different rules at different stages. Men in particular seem to be characterized by different rules at different stages. All men, all the different subsets of men that we looked at take age into consideration at the browsing stage. And what you can see, I wonder if there's a pointer on here. Well, whatever. What you can see is that most of those classes have their maximum value right around 1, which means that they tend to browse women of similar age to them. But contrast that shape with the shape you see in panel B for men writing. What those sort of very, very minimal slopes are telling you is that conditional on browsing a woman, men are largely indifferent to increasing differences if the woman is younger than them. And in particular, there is one group of men that really stand out in this respect. And that's another result that popped out of this. And that's that red group, where you see that red group is a group of men, their average age is around 40, and they tend to write to women who are around 30% younger than they are. And for that particular group, there really does not seem to be a woman who is too young to be written to, conditional on browsing. This is 22% of our men, by the way, if you're interested in knowing exactly how many. For women, just going back for a second, different rules at different stages, women tend to have similar rules at the browsing and writing stages, unlike men. But again, you see some interesting heterogeneity in behavior. I want to draw your attention to this gold line, which is our third class. This is about 18% of the women that we looked at. And these women were interesting because whereas most women tend to write to men who are a little bit older, these women were writing to men who were substantially older. They were on average 10 years older than they were. And what you see over on the right-hand side for writing is they will browse younger men, but those women never write to men who are younger than them. And that's that sharp cutoff you see in panel, what should be panel D, but the lower B. Finally, I want to say a little bit about rules, because one of the advantages of these models is having these sharp cutoffs. I told you a little bit earlier about my class 4 men, the one for whom you can never be too young. It turns out for these men, you can also never be too thin. But in the interest of time, I don't have time to show you those results. But what's interesting about this is if you look at the ages of these men, you can see that younger women are very desirable. And then there's this sharp point at which the line kind of shoots down. It turns out that sharp point lines up within a year to the rule, don't date anyone less than half your age plus 7, which suggests that these men are applying a similar rule to that. And for the women in the gold class, we don't really have a pithy anecdote for those women, except that there's clearly a rule for these women not to write to men who are younger than they are. And these women are also, on average, somewhat older than other women in our data set. I want to show you one more set of results, which is with regard to height. For height, we also see different rules at different stages. Men take height into account at both browsing and writing stages. Women don't really seem to look at height at the browsing decision, but it matters a lot at the writing decision. And the main thing I want to draw your attention to are these really crisp cutoffs that we're getting and the women's writing decision in the lower right-hand panel. What you can see is that different groups of women seem to invoke different cutoffs, but they're all around, they won't write to someone who's less than 4 inches taller than them. They won't write to someone who's less than 2 inches taller than them. Can anyone guess what rule these women might be using? This one I do want an answer. Heels, exactly. If you look at the profiles, not of these women, but of people of profiles on dating sites, which one might do, you see a lot of don't write to me if you're shorter than I am in heels. So that's another rule. Is it a life-changing rule? No, but it's interesting that the model pulled it out. So let me summarize a little bit about what you've seen in these pictures about decision rules guiding mate choice. First of all, we've seen some invocation of sharp cutoffs, which is consistent for rules for partners based on height, no taller than me in heels, and also age. Don't date someone who's less than half your age plus 7. I haven't had a chance with these results to really highlight the deal breakers aspect, but if you look at the change in the utility for the models, what you find is that age is by far and away the biggest deal breaker, followed by the absence of a photo, which makes you 20 times less likely to be considered. We've also seen quite a bit of variation. I mentioned the approximately 20% of men who appear to be pursuing much younger, slimmer women, and there's also a subset of women who seem to pursue older, heavier men. But the final takeaway was, when I first looked at these results, I felt a little bit sad that I had put so much effort into developing this beautiful statistical model, and what it told me was that women don't want to date men that are shorter than them in heels. But then I thought about it, and I thought, this is actually wonderful. I mean, dating is a wonderful context in which to develop these sort of statistical learning models to understand rules, because we have so many rules that we already know about in terms of dating, as opposed to a more ambiguous process where it's hidden from us or we just don't have a lot of information about it. And so, to me, it was actually quite reassuring that the model spit out these somewhat prosaic rules and suggests that it could be usefully applied to areas where far less is known about strategic behavior. So I want to close by just saying a little bit about the topics that I opened up with, that I think that the so-called data revolution presents really unique opportunities for social scientists to study human behavior with kind of unparalleled levels of granularity. But to harness it, we really have to develop a new suite of statistical models that can grapple with and present information about decision processes and other types of social processes. In my case, I found that marketing and decision theory provided a nice theoretical and statistical framework for understanding social science decision processes, and the model that I presented to you today, one could imagine could be applied in other contexts, buying a house, choosing college, ordering food, in which people winnow down from a larger set of options. So thank you very much.
Okay, so if you're trying to figure out whether this is a cat or a dog, it might be a reasonable thing to do to ask a computer to answer that question for you. So this is showing the performance on a standard image classification benchmark as a function of time here. And so even in around 2015, you started to see computer systems starting to beat humans at performing these kinds of classification problems. If you wanted somebody to take a little bit of text that you'd written and then turn it into a continuation of a story, you might be better off asking a computer than a human to do that. This is from a system that was developed by OpenAI. And so this system is given this text as a queue at the top, and then the rest of the text that's on this slide was automatically generated by that system. And it does this in a very impressive way where, all the way through the end of the story, there are words and concepts that were included in this initial queue. But if you want to predict and understand human behavior, then you're still better off asking a human being to do that than asking a computer. So even though we have good AI systems, we have good models of images and text, we don't have good models of people. And there are a lot of reasons why we might care about that. One is that human behavior drives our economy. All of the financial transactions that happen are a consequence of humans making decisions, whether they're in stock markets or people clicking on things on websites. Another is that if you're an engineer who's trying to build some kind of technology that's going to interact with humans, whether it's interacting via voice or interacting physically with those humans, then it's a good idea to have a model of how it is that human beliefs, desires, and intentions relate to the behavior that human beings produce. Because you need to be able to work backward from the way in which people behave to try and figure out what those underlying variables were that motivated that behavior. And that becomes even more important when we're talking about systems that interact in humans in perhaps increasingly physical ways. So this is an example. This is a self-driving car. It's actually, you can see a little Uber symbol here. This was an Uber self-driving car that was involved in a collision. And arguably, this collision was partly a result of not understanding something about human behavior, which is that if somebody can't see, if you can't see somebody, then they can't see you, right? And so there was a situation here where the car was making a decision about pulling out into an intersection, pulling past another vehicle that was waiting at that intersection, while then somebody who they weren't able to see was then making a left turn across the intersection. And so the reason why that other car had stopped was that they'd seen that other person. And so having a little bit of a better understanding about how it is that human beings behave might be the kind of thing that can help you to prevent having those kinds of accidents. So making better models for understanding and predicting human behavior is something that's going to require some kind of interaction between computer science and psychology. And so, as you heard, that's the world that I live in. I spend my time walking between the computer science department and the psychology department on the Princeton campus, and in doing so, thinking a lot about how it is that these different disciplines can influence one another. And so, really, computer science has a lot to offer to psychology in terms of the sort of methods and tools and formalisms for thinking about how it is that we can make good kinds of computational models and how it is that we can collect data at a large scale. And psychology, in turn, has a lot to offer to computer science in terms of decades of expertise in thinking about how to capture the complexities of this kind of human behavior. So what I'm going to do today is talk about two problems, predicting human decisions and understanding human decisions. So very much continuing the theme from the last talk, the focus here is going to be on understanding the decisions that human beings make using this combination of ideas from computer science and ideas from psychology. And so this first project is joint work with Josh Peterson, David Borgen, and Daniel Reichman, who are people who were in my lab. And so the motivation for this first problem is to think about, okay, if we want to understand these kinds of decisions that people are making, can we build better machine learning systems that allow us to make predictions about human behavior? How do those systems compare to the kinds of theories that psychologists developed? How can we use theories from psychology to make those systems better? And so the sort of model of economic decision-making that we use is a classic model that comes from the behavioral economics literature. That is, rather than dealing with people making decisions on the stock market, we deal with people making decisions that look kind of like this. So this is a problem that's called a risky choice problem. So people have to choose between two options, option A, option B. Each of these options corresponds to a gamble. So in this case, option A gives you 16 points with certainty, and in our experiments, those points translate into actual dollars. And option B gives you, 1 point with probability 0.6, 44 points with probability 0.1, and so on. And so what you're doing is basically making a decision about which of these gambles is more acceptable to you. And you can probably see how this is a sort of proxy for some of those kinds of financial decision making. So if you look at this problem, the way that psychologists have looked at these problems is kind of trying to figure out how it is that people make a decision between A or B, trying to come up with theories that allow them to differentiate those. But if you look at this from the perspective of machine learning, when you look at this, you can say, oh, well, actually, this is a relatively low-dimensional prediction problem. Because here we have a bunch of information. All of these numbers are basically dimensions of this problem. So we have dimensions that correspond to the payoffs that are involved, the probabilities of those different payoffs arising. And so we could take these numbers, in this case we have 9 numbers that characterize the decision between these two gambles, and we're going to take those numbers as input, and the output we're going to produce is a prediction about are people going to choose option A or option B. And so that's a well-posed machine learning problem, and it's the kind of thing that we could apply machine learning methods to. And so this was actually done a few years ago in something that was called the choice prediction competition. So a group of psychologists at the Technion in Israel collected a bunch of data on 150 pairs of gambles like this. And then they put these data online, and I sort of posed this as a challenge to people to come up with systems for making predictions about the choices that people make. And the interesting result that they had was that when you took these 150 gambles, you tried to look at predicting the choices that people make, that machine learning methods weren't that great at solving this problem. So in fact, the systems that did the best job of making these kinds of predictions were systems that relied on psychological insight, that didn't work from those raw numbers, but rather worked from a kind of combination of variables which people had come up with as a consequence of looking at the behavioral economics literature and figuring out the kinds of strategies that people might be using. And so their conclusion was that, machine learning has a long way to go, and psychology is essential for being able to make these kinds of predictions. But again, if you're looking at this with a machine learning lens, this number, 150 pairs of gambles, that's a very small number, right? You just heard about all sorts of, big data problems. This is a small data problem. How do we make predictions from relatively small numbers of human observations? And so the conclusion that machine learning methods don't necessarily work all that well here is a conclusion which is conditioned on the fact that you only had a relatively small amount of data. And so the first thing that we did when we started to think about these problems was think about how to scale this up. And so we actually went out and collected a data set which has 13,000 pairs of gambles, so almost 100 times as much coverage of this space of gambles. And the way that these were generated was by actually sort of randomly generating points in this space of human decisions. And this is very different from the way that we normally do experiments in psychology. Normally in psychology, we think very carefully about, I'm going to test exactly this condition, I'm going to test exactly this condition, and we said, no, we're not going to do that. We're just going to throw darts at the wall. We're going to cover this entire space and see what it looks like. And so this is just a kind of visualization of this, taking that 9-dimensional space, reducing it down to a 2-dimensional space using one of the machine learning methods that I'll talk about in a minute. And so the distance between, so each of the points that I'm showing you here is one pair of gambles, and the distance between those points corresponds to the similarity that this machine learning method identified between those gambles. So the red points here are sort of classic experiments that were generated by people using that procedure of thinking very hard about what point in the space to test. The blue points are the largest previous study of risky choice, which was this choice prediction competition. And then the black points are the points that come from our experiment. And so you should be able to see here that we're basically getting much better coverage of this entire space of possible choices, and that we're, as a consequence, going to be able to do a better job of answering the question of what kinds of models work well for predicting human decisions. So this gives us an opportunity to do something that we're not normally able to do in the social sciences, which is to take entire classes of models and just say, hey, does this class of models work well at all? And we can exhaustively evaluate those models against this very large data set. And so we did this by going to the literature and looking at the kinds of models that had been proposed for accounting for people's choices, drawing on the literature in psychology and economics and so on. And so, the first place to start, very classic kind of theory, something that was developed by von Neumann here at Princeton, is the idea of maximizing expected utility, right? And so, a little bit of math here says that the probability you choose option A is going to be based on the sum over all of the outcomes of the probability of that outcome times the utility of that outcome. And so there's this function here, the utility, which translates points or dollars into utiles, the sort of units of how much you value it. And the sort of classic form of that function is something like this, where the idea is that, as the number of points or the amount of dollars increases, the amount that you're satisfied with it decreases. And that allows you to produce phenomena like what's called risk aversion, which is that you'll be willing to take a sure thing, which is actually less than the expected value of a gamble between two alternatives in this case. And so a second theory, again with a Princeton connection, so developed by Daniel Kahneman and Amos Tversky, is prospect theory. So prospect theory takes expected utility theory and then takes it a step further. So now, in addition to this utility function, we also have a probability function, which says that the way that people think about probability may not map directly onto the probability of events in the world. And so in prospect theory, that utility function is augmented by the idea that the form of that function is different for losses, when you're losing money, versus gains. And in fact, it's much steeper for losses than for gains. So people are more willing to take risks when they're thinking about losses. It's something that's called loss aversion. And then in terms of the probability estimates, people sort of overestimate the probability of rare events and then underestimate the probability of more common events. And this is sort of the traditional theory here. But one thing that we can do is rather than being constrained to just the kinds of theories that people have proposed in this space, is actually ask the question, well, okay, if we just didn't know anything about any of these theories, if we just sort of had this idea that you wanted to have something that has this mathematical form and something that has this mathematical form, and then we, in a completely non-parametric way, so making no assumptions about the form of that theory, tried to estimate what these functions look like, we can actually do that. We have enough data to be able to do that. And the way that we do that is actually using some modern machine learning methods where we can recognize that we can write this decision as what's called a differentiable function of the parameters that might characterize these functions. And so we can take something very complex like a neural network model that we might use in machine learning and plug it in for this function, and then we can estimate the forms of those by using this large data set. And we can take that same strategy not just for these models, but now for a much broader class of models. So we also consider the class of models where you say, well, let's take this and then generalize it and say there's some function of those parameters, those numbers that I showed you before, which is going to characterize how much value people assign to a gamble. And so this model says you're going to value each of those gambles, you're going to compare them, you're going to make a decision. And then this model which says, well, let's pretend that we didn't have a value for each of those gambles separately and then decide, but rather we just made a decision by looking at the whole thing together. So you can think about this as the least restricted, most holistic model. This is the one that says, just take all of those numbers and do the best job you can of predicting which choice people are going to make. So I'm going to show you all of these models, and where I'm going to show you their performance is, this is what's called the validation error. So this is the error that they make in predicting people's choices, but on a set of data which they've never seen before. So this is held out data that they've not had the chance to see. And then this is the data set size. So I'm going to show you the performance of these models as they're estimated from these data. And so the first thing we did is go to the literature and look at all of the ideas that people have had for that expected utility model of the form that that utility function takes. And so each of these lines corresponds to one paper that's been written in the last 70 years with a hypothesis about the form that that function takes. And you can see some of them do better than others, but in general, having more data doesn't help you come up with a better estimate of the parameters of those functions. And then here, if we take our machine learning model, we say, let's pretend we didn't know anything about all the work that humans have put into thinking about this problem. We just take the form of that function. We try and estimate what that function is. Then we do about as well as the best of those human theories of how it is that people might make those decisions. And this is what that estimated function looks like. So this is losses, this is gains, and it has this same sort of classic form that I showed you as that function before. And so we didn't need to be smart scientists to figure that out. We could just get enough data and then use relatively dumb machine learning to make that inference. I now added in all of the hypotheses that people have come up with for the form of those functions for prospect theory. And then this is the machine learning version of prospect theory. And this is the form of the functions that are inferred. And one thing that's kind of surprising here is that we don't see these really classic phenomena. There's a sort of slight overestimation of the probability of rare events, but otherwise this function, which is the probability function, is pretty linear. And then here, there's not a big difference between losses and gains, and I can talk more about that for people who are curious about it, but it's actually that having this very big data set, rather than focusing in on some of the weird things that people do, means that it actually turns out that the theory that works pretty well is something that's kind of closer to that more classic expected utility theory. So here I'm just taking these two sort of more flexible theories, and then we'll add in the third one that I mentioned. This is the one that says, okay, let's assume that you're assigning a value to things, but that value is not constrained to the form of something like prospect theory. And it turns out that does slightly worse than prospect theory. And the way to understand that is that prospect theory is actually a really good theory. So it puts a constraint on the space of functions that's a good constraint to have. So it turns out this is a win for the human theorists. Those humans did a good job in sort of coming up with the form that that value function has to take. And then, again, going through the literature, looking at the kinds of models people have proposed, if we take off all of those constraints and we say, okay, now you're just going to try and make predictions from the parameters of these gambles, this is the theory that does best. This is a theory that's called BEAST, stands for Best Estimate and Sampling Tools. And this theory does a very good job of predicting human decisions. It does better than these sort of prospect theory models and so on. But if we take that completely unconstrained machine learning problem and we just take the best machine learning system that solves that problem, it does significantly better than the best human theory, provided we have enough data. And so that observation that we have to have enough data for this to happen is important. So just to sort of make this salient, this is the size of the previous largest data set that existed in this domain, right, in terms of the number of problems that were used. And so if you look through this slice here, at this slice, the humans are beating the machines, right? So with the small amount of data that we had, humans did a good job of solving this problem of coming up with theories that would allow us to predict human behavior. But as we get more data, then the machine starts beating the humans, and this gap here tells us that there's systematic variation in human decisions that aren't accounted for by any psychological theory. And one way of thinking about this is that what it tells us is that our psychological theories are just way too simple. That we've been used to living in a world where we had limited amounts of data. Those limited amounts of data allowed us to get away with having simple kinds of theories, and there's a lot more complexity in human behavior that we haven't captured yet. The other thing that we can do here is actually ask, well, can we make that machine learning method better using a little bit of psychology? And the answer to that question is yes. So if we take that machine learning method and we train it on data that's generated from this psychological model before it sees any human data, and then we train it on the human data, we get this purple line here. And this is a model that does better than any default machine learning model and better than the psychological theory for any amount of data. So this integration of theory and machine learning methods actually gives us a tool which is much more powerful than either of those independently. Okay, so what are we going to do about this gap? We've got this sort of clear observation that there's things that the machine learning models are getting that the humans aren't. How are we going to solve that problem? That's the topic that I'm going to tackle in the second part of the talk here. And really, part of that problem is that the psychological theory is something that gives us a way of understanding those decisions. The machine learning theory gives us a way of predicting the decisions. And we want to work towards having something which is a psychological theory that gives us that kind of understanding, but also allowing us to get the same kind of precision in predicting human decisions that we got from that machine learning model. So the domain where I'm going to think about this is actually surprisingly similar to one of the examples that I used in setting up the talk, which is the kinds of decisions that we might have to make when we're driving. And so the data set that I'm going to use here is a data set that's called the moral machine data set. This is data that was collected by a group of people. The leaders of this study were at MIT. And the part of this data set that I'm going to look at involves people making decisions about what an autonomous vehicle should do. And so the setup is there's a vehicle, it's speeding towards an intersection, right? On this crosswalk, we have a bunch of people, and the vehicle can either continue straight, in which case it kills these people, or it can swerve, in which case it kills these people. And so the question is now, what should the autonomous vehicle do? Right? Yeah. So the assumption is that you have to do one of these two things. And so they actually collected like more than 10 million human judgments for these kinds of scenarios, varying what the composition of these different groups of people were. And so the question we want to engage with is, can we actually build a good model that helps us understand what's going on in making these decisions? So again, we can start with a good sort of simple psychological model, and the model I'm going to start with is what's called a rational choice model. This is going to assume that there's a value for each of the lives on one side and the lives on the other side, and a reasonable starting point is a sort of utilitarian model that says that each of those lives has some value, and the aggregate value of all of the lives on one side is the sum of the values of all of those individuals, and likewise on the other side. And then when you're making a decision, you're just sort of weighing one side versus the other. So this model does okay. You can actually make it a bit better by adding some psychological principles, what are called deontological principles, sort of moral laws that people seem to obey when they're making these decisions. So for example, people who are crossing legally are favored by people when they're making these decisions. If you have one person who's crossing legally and one person who's crossing illegally, it's more permissible to hit the person who's crossing illegally. You should think about that next time you're crossing the road. And likewise, in this kind of scenario, there's actually people prefer not to swerve. So they think that swerving is a kind of moral action, right? Whereas continuing is a kind of inaction. And so there's a kind of moral prescription against like taking an action that then results in these additional deaths. And so when you add those things in, it does it a little bit better. But when we contrast this with a neural network model, you know the story at this point, right? So this is, again, here's our utilitarian model. So these are just to give you a sense of what we're doing here. So this is, we sort of all lives being equal weight. It gives us, an accuracy of about 64%. This is If we differentiate between animals and people, that gets us up to about 68% in terms of predicting these choices. A utilitarian model where we estimate the weights for all of those different kinds of people separately gets us a little bit better. Adding in these deontological principles does a little bit better, but then our machine learning model, just based on a generic neural network that's taking as input the identities of the individuals on either side, beats the best psychological theory that we're able to come up with here. And so the question is, how do we close this gap? How do we make our theory better? And the big problem here is that often when we're analyzing things like this, we just don't even know what the factors are that we should pay attention to. We don't know what the variables are that are relevant to this decision. And so one way that researchers proceed when they're doing this, they do something that's called exploratory data analysis. One kind of exploratory data analysis is to focus on the errors that the model is making. So you look at the errors that the model is making, and then the biggest errors suggest something which is missing from your model. But the problem is when you have something like 10 million human choices, the errors that you see could just be a consequence of noise, right? If you get enough data, the biggest sort of noise-based variation that appears in that data gets pretty big. And that's actually what we see when we look at this in this data set. So this is, if we take that best psychological model and we look at the residuals to data, these are the different scenarios that have the biggest residuals. So this is one where the data says that 99.4% of the time people chose to kill the people on this side of the road. The choice model says that shouldn't happen. It should happen 11% of the time. The neural network says that should happen about 17% of the time. The residual here is big, right? But if we look at it, this is actually kind of a weird scenario. This is people saying that you should kill 4 humans rather than 4 cats. What's going on, right? We emailed the people who did the study. They had no idea what's going on. It's some kind of weird error. Something maybe happened by chance. Something maybe went wrong in the experiment. But this particular scenario is one that it just seems like the data's wrong. There's nothing wrong with the model, it's the data. And the same thing was true for these, but to a lesser extent. But one observation you can make is that actually the choice model and the neural network kind of agree in this situation. And the fact that they agree might be a hint to us that this error is not one that we should be paying a lot of attention to. So based on that observation, we developed an approach that we call scientific regret minimization. This is kind of a joke to people who are in the machine learning community, but the idea is that we should only care about those errors that we could have predicted, right? And so this is an error where if we think about our neural network model as being the best that we could do in predicting these data, the fact that the neural network model also made this error tells us that this is an error that we shouldn't care about so much. And so the idea is that what we do is we take our machine learning model, we fit that to the data, and then we look at the errors that our theoretical model makes with respect to the machine learning model rather than looking at the errors that it makes with respect to the human data. And we look at the biggest errors like that. And that's actually a way that we can diagnose what are the features that the neural network model has discovered that our theoretical model is missing. And so when we apply this in the context of this problem, now we get our biggest residuals look like this. So this is here, the car is going down. It's going to, here it hits a human versus a cat. The data says that 30% of the time people choose to kill the human. The neural network says, about 30%. The choice model says 70%. And the reason is that it's quite subtle, but the human being is crossing the road illegally, right? And so that constraint that we had that, illegal crossing is something that should make you, so the cat is crossing perfectly legally, and it says, oh, we've got a situation where we've got someone crossing legally, someone crossing illegally, then it's reasonable, even though cats are valued less than humans, it's reasonable to save the legal crossing cat, right? But that is not something that humans do. And so that allows us to identify that, in fact, in any scenario where there's a sort of general principle here, which is true of all these residuals, in scenarios where you have humans versus animals, then people will choose to save the humans. And we can add that as a factor into our model. And then we do it again, and we identify more factors and so on, and we sort of repeat this process. And so we can use this as an iterative procedure for pulling out the variables that seem to matter to human decisions. And then, because this is an exploratory technique, we then run additional experiments that check that, in fact, that is true about human behavior. And so when we do this, we discover some interesting subtleties about people's moral decisions. So as a consequence of doing this through multiple iterations, we can discover some complex kinds of high-order effects. So I mentioned the first order one here, that if you have to choose between a legal crosser and an illegal crosser, then it's more morally permissible to hit an illegal crosser, unless they're children. right? Something which is revealed through this analysis, that you have to include this additional interaction in the same way that was relevant to animals. There's kind of a notion of responsibility that applies to whether you're making the decision to cross the road legally or illegally. And if you're an animal or a child, then that doesn't apply, unless they have one adult with them. Right? So if you have a group with lots of children crossing with one adult, then it matters again whether they're crossing legally or illegally. So discovering this kind of third order interaction is something that, had we done this in a completely naive sort of standard way of analyzing these data, would have required us to have a model that had about 15,000 predictors in it. But by doing it through this procedure where we're pulling out these features, we can actually identify this within about 3 iterations of doing so. And we also discover some interesting unexpected interactions that fall out. So for example, if you have a situation where you have someone, and it's not clear whether they're crossing legally or illegally. So it's sort of ambiguous, you can't see the sign, you don't know if it's a legal or illegal crosser. If it's a woman, then the rate at which people end up choosing to hit them is basically exactly in between the rate of hitting legally crossing women and the rate of hitting illegally crossing women. But if it's a man, then it's basically people assume that they're crossing illegally. So men don't get the benefit of the doubt in these circumstances where you have to make an inference about whether they're following the rules, right? And so these kinds of principles that you pull out are exactly the kinds of principles that you'd want to be able to identify if you're thinking about using something like a machine learning system to develop your self-driving vehicles and thinking about how it is that you want to regulate and legislate those systems. Because some of these are things that seem like maybe the sorts of things that you'd want to think about including in your systems. And then some of these are things that you have to think hard about whether those are principles that you want to mathematically encode in a system which is going to be driving around on roads and making decisions about who it's going to hit. So conclusions here. So combining computer science and psychology gives us a way of building predictive and explanatory models of human decisions. And I think these are things that have, as you saw from the previous talk, very broad applications. But I think to repeat the conclusion that you heard previously, there's only a tiny fraction of the relevant data that we could be using for answering these questions that we're actually using. And there's a huge amount of data out there that I think, in many ways could give us more insight into understanding how it is that people's minds work than the entire history of research in psychology. And so this is an exciting moment for people who are interested in these questions. I see a key frontier here as being one of building the tools that are going to allow us to do this kind of large-scale data collection and analysis to allow us to get the insights that are hidden away in these big data sets. Thank you.
We have plenty of time for questions. I will get us started with a few points of discussion and maybe controversy, and then we'll open it up to the folks in the audience. So first, I wonder if you could talk from your own perspective a little bit about the misconceptions about your own field that you think most frustrate effective dialogue between the social sciences and research in machine learning and artificial intelligence.
We have mics. Okay. So
As they relate to these two talks, or?
Not necessarily.
I think the big one for me is what I was talking about, which is that if you ask a psychologist how to answer a question about the mind, they say, give me 200 undergraduates in 3 months and I'll get back to you, right? Whereas we have all of these other kinds of sources of data that, if we can work out the right ways of working with them, would allow us to answer our questions, I think, far more effectively.
So the misconception is really about the adequacy of traditional research methods to some extent and traditional data.
So I'm going to answer this in a particular way, and then you can push back if it's not, but I think, I don't know if it's a misconception, but I think that the methods and data that sociologists have encountered for the last 50 years have really shaped the types of questions they ask. And so I think that a lot of the questions that we formulate are variables-based questions, or questions about associations between attributes or individual characteristics and outcomes. They're not necessarily process questions. I'm not sure if machine learning can answer the process questions immediately, but I think that that would be a more fruitful place to meet, because that's really where the rubber hits the road in terms of the complexity of the data and what can be learned from it.
I think it's really that we just need to talk to each other, right? That I want, to push in the direction of working with larger data sets, and you want to push in the direction of working with models of process, and those are things that sociologists and psychologists historically, respectively, have been good at.
No, that's right. And I also think that a place where the data become really important, and I think you were alluding to this in your talk, is that human behavior is incredibly noisy, and you need sometimes a large data set to sort of push through all of that noise.
So you remember I said in my introduction that we hoped that collaboration would arise from these conversations. You can see it's apparently happening already. So actually, Elizabeth, your point provides a beautiful segue to one of the other points on which I wanted to probe the two of you. And that is that in your talks, both of you focused on individual human decision making. And while certainly many of the decisions you discussed are social actions and have social consequences, running over a large number of cats has social consequences, the social sciences, of course, also take as their subject matter collective behavior, like participating in social movements, things like the social production of the context in which people are making these decisions, or the principles that guide our action. So I wonder if you could talk a little bit about how to move from these understandings of individual decision-making to some of these more collective phenomena that have been kind of the bread and butter of a lot of social science research.
Right. So there's two ways of taking your question, and one of them could be the fact that when we think about individuals making choices in isolation, we're really thinking about sort of a brain in a box, right, or brain in a jar. But in fact, people's choices emerge in social contexts, and those contexts themselves are important. I guess one thing that's been useful for me in thinking about that is the fact that there's a large literature, for example, about behavioral nudges, right? And typically, when people talk about a decision environment, they're talking about things like putting apples before chocolate cake at a cafeteria. But of course, one thing that comes up in social science is that for a lot of decisions that we make, what other people are doing is the social environment. That's kind of, and I think in that sense, some of these models could potentially be fruitfully applied to sort of processes by which individuals' decisions are influenced by the choices of others, by taking into consideration the feedback between the decisions that people are making and the contextual influences that are helping them. But there's a second way of thinking about what you're saying, which is more, can these models help us predict collective social processes, not individuals as influenced by other individuals? And I don't know, that's a harder one. I'll have to think about that.
Yeah, I mean, as a psychologist, I'm a little uncomfortable talking about, things that go beyond small groups of people. But one of the things that we've been doing in my lab is building the tools that allow us to run behavioral experiments with those small groups of people. So using crowdsourcing services like Amazon Mechanical Turk and other methods for recruiting people, we have access to thousands of potential research participants. But the way that a lot of research is still being done in psychology is very much using the same kind of model that we had when we had physical labs that those people had to come to. And so, whereas when you remove those constraints, you can study situations where you have people interacting with one another, where it's involving as little as a single decision, and the decisions that people are making are influencing the decisions that other people make. So we built software that allows us to run those experiments, and we can look at things like processes of cultural evolution and how information changes as it's transmitted from person to person, or even simulating sort of small-scale interactive societies, provided those societies exist for 30 minutes to an hour, and that's sufficient to allow us to answer the questions we want to be able to answer. And I again, sort of view that as part of the future for the kinds of things that we should be thinking about doing.
It's terrifically exciting. So I'll ask one more question, then open up to the floor. And once again, this is teed up by some of these points that both of you raised about the ways in which these decision environments are constituted by the actions of other actors. And indeed, one of the reasons I think many folks are interested in building better models of human behavior is to facilitate interaction between human agents and some kind of computational agent, whether that's to recommend movies for us to watch, or people for us to date, or to prevent self-driving cars from running over a large number of people. But at the same time, the existence of these computational agents acting in our environment also helps to shape the behaviors and the preference structure and the decision rules and so on of human actors. So is that something that we should be thinking about? I mean, okay, yes, it is. So how do we think about that kind of feedback loop, and what can we do to prevent the unintentional distortion of human decision making by inadvertent structuring of the decision environment?
I would turn that around and say, what can we do to better support human decision making through advertent structuring of the decision environment? So, I mean, a lot of the work that we do is really focused on the idea that when you see errors in human decision making, those are often a consequence of limited resources, right? Limited cognitive, computational resources. Like human beings have with us only the compute that we're able to carry around inside our heads. And so many of the decisions we have to solve are situations where we don't have the compute to be able to solve those things effectively. And so you can think about how can you help people do a better job with those things, and not being able to put more compute inside people's heads directly. The way you do that is you put compute in the environment.
Right.
So by structuring environments in ways that help people make decisions. And again, that's a problem that we work on, but the basic idea is that if you can describe human decision problems in terms that you can get computers to partially solve, then you can use those partial solutions to then decide what pieces of information are easily accessible to people in a way that helps people then find better solutions to those problems.
I actually think there's a lot of promise in these systems for helping people make better decisions because every individual, I mean, the types of problems that I work on, what neighborhood do you end up moving to, what kind of partner do you find? They're not decisions where you get a lot of practice. Most people don't date thousands of people before they choose their partner or look at thousands of houses. You have limited time, limited capacity, but a lot of these systems have a lot of other people's experiences coming to bear. And if there's a way of helping those experiences inform, I mean, I think that, in the same sense that Amazon tells you if you like this book, other people who like this book could also like, there's a lot of ways in which you could draw on other people's experiences to make better decisions. Because that's the more positive version of the
I love the positive and optimistic spin. So
I hope we don't get reviews on our romantic partners.
Speaking of allowing other people's experiences to inform the conversation and improve it, let's open the floor to questions from the audience. And I think there are mics running around. So, yes.
Thank you. So thank you so much for those talks. I really appreciated them. And I recognize that this idea of quantifying at scale social science questions is very new, and a lot of work has to be done before it's clear what are the right research questions. But my question is for both of you, what you're doing to predict the kind of problems that may involve your data and how much it reflects the research question that you think you're asking. So in other words, at this stage, so few people are doing this kind of work that maybe any result teaches you something. But past a certain point, if this is really reimagining what social science will be, we want to make sure that we're asking the right kind of research questions to the right kind of data. So, for example, asking 1 million people on Mechanical Turk what they think they would do to the trolley problem isn't really going to crack the nut of autonomous self-driving, or even tell you much about how in actual cars people make decisions, if that's even what they're doing, as they reflexively respond to a situation where they might need to kill people. That doesn't mean that it's not interesting what you're doing, right? But it seems to me that there's a presumption that if you get a large enough data set, the nut can be cracked, when in actuality, the data is a certain kind. This relates to the third question that was asked. Similarly, I agree that people should be given the opportunity to reflect on this kind of like mass collected data about these very social questions, like how people choose when they're online, the kind of neighborhood or partner that they might be interested in. But it seems to me that what you are ultimately going to want is some qualitative data to complement what you've found, so that, for example, these 40-year-old CADs that are looking for young, skinny women, how much is it that they are looking to marry someone to have children, or how much is it that some other factor is affecting their particular decision to favor younger women over women their own age. That's just obvious, right? I mean, I'm not saying anything that you probably haven't thought of yourself, but again, the assumption is that because you've suddenly got this trove of micro decision data, that you're going to be able to find out something that is holistically valuable about human behavior. In some sense, it probably will be, but in other sense, it's an artificial environment. And what are you going to do about the fact that your research question is so much determined by the data that you have?
Well, there's a lot of things in that set of comments, and I mean, I think the last piece, I want to push back a little bit, because I don't think these are artificial research environments. I think people are making consequential decisions about their lives in these environments. I think that the second thing is that there's two ways of thinking about this. One is sort of like, what is the social good of this research? Is it helping us? But I also think that another piece of this is about, can it change the way that we go about our work? I think for a lot of social scientists, in the absence of process data, they sort of had to fall back on simplifying assumptions that were wrong and potentially had negative policy consequences. So, for example, people who studied college choice, an implicit assumption is that people knew all salient attributes of every single college in the United States, which is, nobody believes that, but in the absence of another statistical model and data, you're forced to make those kinds of assumptions. And so I think understanding winnowing processes and seeing opportunities presented to them can lead to better models which have both scientific consequences and also policy implications. In terms of the piece about qualitative data, I absolutely agree with you. I think big data is richly textured, but for example, one critical thing that's missing from all of these data, I have data on 4 million people making decisions on an online dating site, every single message they wrote, all their browsing over the course of a year. It's an enormous amount of data, and yet I know nothing about what's going on in people's heads. I don't know how they construct their own process, and I don't know what's happening to them off of the site that might shape their behavior. And so there's a lot of pieces of information that are missing from these environments. However, I think for people who are used to working with statistical models using large-scale data, there's a big difference between sitting with a survey asking someone to report on their attributes and actually having some sort of information about the activities that are going on that gave rise to those attributes.
Yeah, I mean, I agree that I think, I actually see one of the merits of this kind of approach is exactly that it allows us to engage with more naturalistic kinds of problems. So, if you were concerned about the level of abstraction that was involved in the things that I presented, that's already an order of magnitude better than the standard laboratory experiment. And part of the reason why it's possible to do that is because operating at scale gives you much more flexibility in the way that you formulate your experiment. And so, we also do things where, like the entire psychological literature on how people learn categories has been based on stimuli that are like circles with lines in them, because having a two-dimensional stimulus makes it very easy for you to define a mathematical model of how people are solving that problem. Whereas when we run those studies now, we do it with real naturalistic images that are actually sort of interesting, complex stimuli that require 4,000 dimensions to represent, and the way that you get there is by being able to scale up the amount of data that you're working with. And so I see this as an evolution in the direction that's going to hopefully end up being more satisfying.
Hello, thank you for your talk. So my question is about, so our behavior, including mate choice, house buying, school choice, etc., are becoming increasingly predicted and modeled by governments and companies, and sometimes they're creating self-fulfilling prophecies, kind of similar to what you said. And these self-fulfilling prophecies come up in all the wrong places, like predictive policing, recidivism scores that many times point police officers to neighborhoods, minority neighborhoods that have increased, are at a high risk of people doing violent crime or small-time crime. And that creates a self-fulfilling cycle. And so in instances like these, are the models inherently problematic, or will more data solve the problem and maybe improve this?
That involves more than small groups of people, so maybe that's...
Well, I think that, sorry, can you repeat the last part of your question? Will models?
I was wondering about how, like, are the models themselves problematic? Like, for example, predictive policing specifically, where you have like zip codes where police officers are sent to, investigate more often. So obviously there are higher arrest rates, and so then police keep going back to that place.
I don't know if the models are themselves problematic. I think that the world is I mean, they're being applied and they're learning from a problematic world in which there are differential treatment and bias, and so the models are going to reflect that bias. What's interesting is I think that's a great place where I think we need social scientists to come in, because social scientists are computer scientists may not have spent 8 years of their PhD studying bias, and it's the social scientists who often have insights into what the underlying processes were, or at least some of it, that gave rise to those data. And so I think it's not that the models are wrong, it's that there's things about the world that we think are unfair, and then the model's going to reflect that unfairness.
Yeah, I guess you could think about something like the process that I was talking about as a way of surfacing what are the features that those machine learning systems are using, in a way that those can then be things that you make intelligent decisions about whether that's a reasonable thing to use, right? So, being able to do something where you're able to make a completely interpretable, sort of linear regression model or logistic regression model or whatever it is that's allowing you to make those predictions, but with a precision which approaches that of the uninterpretable machine learning system, is a way to then be able to develop, kind of at least have a debate about what are the things that we want those decisions to be based on. Yeah.
I had a question, but I was going to make a comment on that, because I've recently retired and worked in criminal justice for 34 years and was in ComStat meetings. So the models themselves are helpful. They're not problematic. It's when they've gone off the rail, when you've seen this most often happen in New York City and actually locally in Trenton, is when folks were given incentive to hit certain targets, and they had to hit those targets, and they would hit those targets by making a certain number of arrests in their district, or in some cases not encouraging folks to report crimes to decrease the reportable FBI numbers versus the ones that were citizens' complaints, those sorts of things. So that was really more a governance problem than a model problem. The models were actually relatively helpful at deciding where police resources would go, is what I would say. So that was my personal experience, so I figured I would chip in with that. But my question was, when you're doing these models, we know a lot of, and my background is in social sciences besides that, so a lot of human behavior, as you saw in the utility model and the problems with that, is not strictly utilitarian. It's governed by emotions, and certain emotions have outsized effects on people's behavior. Is there any attempt to boil or categorize these features in your model to predict behavior, like repulsion and things? And we saw recently in the election the huge swing where folks have almost like a mass sort of contagion, where folks get a feeling and it drives other behavior. So my question was about the role of emotion and how that's interpreted.
I guess that's about small numbers of people, so that's
That
really
is
great. So, I mean, not in the work that I presented here, but I don't view emotion as being something that is divorced from rational models in general. In fact, I see it as a consequence of a kind of rational design of a decision-making system, right? It's a component of the way that we are implementing a system for solving certain kinds of functions. And so, and there are nice rational analyses that are given of things like love and anger as emotions that make a lot of sense from a game theoretic perspective. So, I mean, I think those are things that, even though they feel visceral to us and hard to express formally, are things that we can capture in these kinds of models. One of the projects we're doing in my lab at the moment, motivated by election-related things, is looking at motivated reasoning, right? So just giving people a very simple task where they just have to say, are there more blue dots or green dots? And depending on whether they're getting money based on the number of blue dots or the number of green dots, they give you different answers. And so we can nonetheless analyze that and then make models that tell us, okay, now if you have a population of people who are acting in this way, then how, as information flows through that population, is it going to change, and how is it going to become biased? And we can show that it gets more biased. And then using these same kind of computer science ideas, we can say, now if you know that that's the sort of biased sampling process that you're experiencing, how do you correct that, right? And you can use the math to tell you how you need to think about sort of structuring interactions in the population in order to mitigate those kinds of biases. So I think for all of these things that are intrinsic aspects of human behavior, as hard to express mathematically as they seem, I think expressing them in those terms is something that gives us the tools to think about how to engage with them and to engage with some of the, as you're saying, like unintended consequences of things like technology.
And I think that some of the models that were presented tonight could actually incorporate some of those things. For example, the the risk aversion that Tom was talking about. You can imagine that there's also a literature in psychology about how bad things are, people feel bad things more strongly than good things, right? And so that's a sense in which there's an emotional reaction, but it can still be encoded in a similar modeling framework.
Boy, I really loved your talk, Tom. It was fantastic. For the last 40 years, I've been trying to help patients make a better decision. So I give them this model that they're in the middle of the street and 10 cars are coming at them. One is coronavirus, one is flu, one is heart disease, one is dementia, one is diabetes, one is a family member dies because you didn't spend enough time or you didn't take your statin and you end up with a heart attack, and they have to make a decision. And then I tried to communicate to the patient through the Myers-Briggs model. The extrovert wants me to talk, the introvert wants things in writing. The thinker always makes their own decision. They think of me as just a consultant. The spontaneous person says yes, and then they don't follow through. The organized person says no, and then they follow through. And it's an endless battle to understand the psychiatric processes and decisions. That person worries more about corona, doesn't get a flu shot, dies of flu, doesn't take their statin because they've been washing their hands for 3 hours, and dies of a heart attack the next day. So you now are in the world of Stanley Milgram for me, of those great decision trees. But I want to see you apply this model and your algorithms of the mind and your manifesto into computational, ipsative, long-term decision trees in patients making better decisions for their health. And I see it as a value-based decision more than anything. In particular, looking at history, Kant is writing all this, what'd you call it, deontological decision-making?
Yep.
And then the next thing you know, Heinrich Heine says, watch out, the Germans will aggress to a Greco-Roman culture and kill everybody and kill every Jew. And he ends up with a better moral decision rule about what's going to happen in Europe than Kant, who's this rationalist. So we must come into some better long-term 60-year studies that are part of Medicare, 80-year studies, 300-year studies that continue to look at all your factors. So I want you to comment on the long-term modeling process.
Yeah, I mean, you'll be pleased to know there's a field called computational psychiatry, which is sort of starting to come together, which is really trying to take exactly these kinds of cognitive models and then apply them to some of these sorts of questions. So my colleague, Yael Niv at Princeton, is somebody who's doing a lot of work on those kinds of questions. And it's her name. Her name is Yael Niv, N-I-V. And so she's somebody who's working in this field of computational psychiatry. But it's, I think there's a lot of potential there to think about. I mean, in the work that we do, thinking about the ways in which these kinds of decision-making processes can go astray, and how decisions unfold over time, and all of these kinds of questions in more precise terms. Yeah.
I'll just add to that at the Institute for Pure and Applied Mathematics at UCLA, we recently had a workshop on computational psychiatry, and they usually put the videos online. So we maybe have time for one or two questions.
Thank you. That was both were extremely interesting. I do have a question about Mechanical Turk. And Mechanical Turk would seem to be a better sample of humanity than American sophomores. So the question, though, is how much is known about Mechanical Turk? How representative is it? Is there some bias in getting people who are earning little bits of money by participating in these surveys? Has any studies been done validating results using Mechanical Turk?
Yeah, I mean, there's a lot of work on those questions. So, and to be clear, so I talked about, the first study I talked about used Mechanical Turk participants, and the second one was just people who had seen this study and it was shared on Facebook and so on. So they got a lot of people coming to the website, actually from all different countries all over the world. I think they had 100 different countries in their final sample. So that was a pretty diverse sample, but again, it's like constrained by people who are on the internet, right? And so that's a pretty big constraint. I mean, in terms of Mechanical Turk, it's better than what we used to do. It's not as good as other things that we could do, and so it's kind of a matter of again, like how easy it is to do different kinds of research, but. It's a surprisingly broad range of people in terms of age and socioeconomic status. There's definitely a dedicated group of people for whom that's their main thing. One of the things that we've noticed when we run experiments is they are very financially motivated and savvy decision makers. So one of the things that's critical in running our experiments is just thinking about how we structure the incentives. They're really thinking about it as their job and making decisions about, am I making the best use of my time? Could I making more money doing another task, and so on? And so those are things that affect their behavior in the way that they affect behavior of all of us. So if you want to see some sort of studies looking at that, there's a study by Mason and Suri, S-U-R-I, which is a pretty good early overview of what the Turk population looks like. I don't know if anyone had any other studies they want to recommend. Yep.
So one of the great insights from micro-interactional social science, and this is something you can use in your everyday life, is that the design of the questions that you pose reveals to your audience the preferred answer to that question. So I will ask if there are any more questions. One last question.
Thank you so much for both papers. So I think this is a question for Thomas, but it draws upon Elizabeth's paper. So when you're designing these experiments, it strikes me that you're turning things that we usually encounter ontologically in the world in other forms into, you're transforming them. So for example, the legality-illegality distinction, we usually encounter either linguistically, so using Elizabeth's terms, we usually encounter it more in a slope in terms of a range of arguable possibilities rather than a cutoff. Or we encounter it politically in the sense that illegality is bandied around in immigration and so forth in lots of ways, and used to categorize people in ways, sort of lay and biased ways. So in that, taking account of the way in which we encounter that distinction in other settings, in your experiments we encounter it as a cutoff point, more or less. It's like a switch. So is it possible to design the experiment to kind of reinsert this elasticity at scale so that the object can retain its slope-like character and also take account of these historical characteristics, the fact that people might interpret illegality very differently at one moment in political history, even month to month, as opposed to another?
Yeah, I mean, I should be clear, I didn't collect those data, so they were collected by this, this group, and that whole data set is actually publicly available. So one thing that would be interesting to look at, we didn't include as a variable in our analyses, but one of the variables that they looked at in their original analysis was country of origin for the people who were answering those questions. And so you can imagine that some of those notions around legality and illegality are things that might vary across nationalities, and it would be interesting to look at whether there are other factors that explain those kinds of variations. But I think in principle, yeah, I mean, I wasn't presenting this in terms of saying, this is the definitive way of answering these kinds of moral questions, but rather here's an opportunity that we have to think about how to build better models of decision making as a consequence of this data set having been collected. But I think if you wanted to do a better job of that, then that's certainly a dimension that it would be worth thinking about. Yeah.
Okay, well, I will thank you all for your wonderful attention and questions, and ask me to, join me in thanking our wonderful speakers. Tom, Elizabeth, thank you so, so much for your terrific talks.